Welcome back, and let's continue the discussion on this internal reacting system. So, we have already discussed the different aspect of the gas turbine engines, and then we looked at the chemical rockets and also the ramjet kind of engines in a brief. Now, we will continue from here the discussion. This is where we stopped the chemical rockets. Now, we look at the non-equilibrium expansion. So, how that impact. So, non-equilibrium expansion. So, equilibrium composition, essentially composition which is equilibrium compositions, it depends on pressure and temperature for a given fuel and equivalence ratio, and also it may possible that it may include large quantities of dissociated material. Okay. Now, when you go to the exhaust nozzle, the dissociated compounds tend to recombine because of temperature drop. So, in nozzle, the dissociated compounds tend to recombine due to temperature drop. Now, what happens? This exothermic recombination reactions may act as a heat source in the flow. So, these are this recombination process, the recombination is exothermic. So, they can act as heat source in flow. Now, we can see how this dissociation energy is before and after the equilibrium expansion for a. So, we take an example of let us say H2O2 mixture and see how that actually affects. Let us say we put a diagram here and some axis could be 20, let us say 40, 60, 80, 100. So, this is your energy percentage. And we get some, let us say block here, and so there would be 1, so this could be 1, this could be 1, so this is what it is. So, this is for combustion chamber at 40 atm and 3500 degree Kelvin. So, this is your electronic energy 0.1%. So, this could be 26.6%, this is vibrational, so which could be 16.6, rotation which could be 19, this is primarily translation which is 37.8 roughly like that. Now, we can look at the nozzle exit and get a block like that. This is nozzle exit which is 1 atm and 2500 degree Kelvin. So, somewhere this is here, then this is here, this is here. So, this is 46.4, this is my translation which is 22, rotation 12.7, vibration 9.2, and this is 9.7%. So, this guy and here and this guy here, this is the dissociation energy. Okay. And this electronic energy would be here for small percentage, and this is the kinetic energy. So, you can see the differences here. This will illustrate the relative importance of these dissociation energies before and after an equilibrium expansion. See, this H2O2 mixture is stoichiometric. So, this is an H2O2 mixture, this example, and they are in stoichiometric. Now, if you have a product to maintain the equilibrium composition while expanding, recombination reaction should be fast enough to keep pace with rapid expansion. Okay. Now, the expansion process is rapid. So, expansion process is rapid. So, that is why this condition is not always met. Now, in a limiting case, one can have tau of recombination which is greater than the expansion. So, this is your exactly frozen flow condition. These things are happening inside the rocket engine. Now, there is a difference between equilibrium and frozen flow and for different propellants. So, that is there. Now, the problems in the rocket engines, there are some problems in rocket engines. One of the issue is that instability, as I mentioned there. I mean, obviously this exists both in liquid and solid case, but solid case it is more compared to liquid case. Then you have low frequency oscillations which is roughly 100 Hz due to the coupling between combustion and the feed system. Obviously, you will have high frequency oscillation too, high frequency oscillations. This is something called thermoacoustics or coupling between combustions and the acoustics and flow field, something like that. Then you have some things very specific to the solid propellant rockets, which is like in solid propellant burning rate is very sensitive. Burning rate is very sensitive to pressure and velocity. Then you have energy release and propellant velocity or the pressure pattern that causes non-pneumatic and interact to the produce sustained oscillation also. So, there could be oscillation from other sources. and this comes from that energy release, and that coupled with the propellant velocity and or the pressure pattern that develops inside the chamber. Now, these oscillations lead to high rates of erosive burning, and that could also, so this could lead to erosive burning, and that may change the chamber geometry to stable burning or may lead to engine failure. So, this has both the aspect. It could lead to stable burning or engine failure. So, both are possible. Then the problem is, as I mentioned, the burning rate of solid propellant. So, this is not very controlled. This is not controlled or not easy to control, and in liquid case, obviously one of the issue which is very well known and well common is that atomization or mixing. So, these are some of the issues which actually exist even today. I mean, and it requires a lot of attention to control this kind of issues. Now, we will move to, so this is our steady flow pattern of the, I mean basically the engines which comes under the steady flow conditions. Now, in the unsteady there are, we can look at this SI and CI engines, which are compression ignitions and spark ignition engines. So, they are also internal combustion system. They are also internal combustion system, but unsteady flow. Now, SI engine has a cycle which is known as Otto cycle, which is or this is basically for your gasoline engine, petrol engines, and CI engine is basically your compression ignition engine. This is for diesel engine cycle or ACCI engine cycles. So, they have these things, and one can see schematically how these two things are different. So, let us say you have a spark plug sitting there which comes through, then you can define your combustion chamber like this, where you have a piston head and this is the piston movement which happens, and this portion is your the flame. And the other case you can have this is my piston head. So, here these are my this is spark plug, this is my CI engine or gasoline engine, this is SI engine. This is spark ignition engine, this is compression engine. So, this would be your gasoline, this is diesel. So, this is your P mixed charge and this is non premixed charge, and this could be your flame surface. So, that is my flame front, this is spark plug and inside that you have fuel plus air mixture. Here it is air only. This is my fuel spray flame, and that is the fuel injector. So, there is a difference you can see inside that. There is a fuel and air which is already premixed, they are sitting there, and this case it is only air which is compressed. So, the working principle is quite different, and that is why the problems which will arise in each of these case, they are also quite different, because this particular case in the SI engine or the gasoline engine, there is a chance of auto ignition or knocking or something like that because of your fuel air premixed, but in the diesel engine you do not have the possibility of knocking or all this, but emission level is quite high. So, one can look at some schematic of this 4-stroke SI engine. This is our 4-stroke SI engine operating cycle. Now, this is first is the intake stroke, that means it comes down. So, air comes in, this valve opens, air comes in. So, the volume increases here, basically the rather it is a mixture comes in, then compressor, it is compressed, and towards the end of this compression you actually ignite that through the spark. Then when the combustion takes place, it actually allows this piston to move. So, the expansion takes place, and then finally exhaust stroke, these valves open and things go out. It's a simple operating principle, and this you can typically see in your 4-wheeler car which are on road. Even today they operate in this kind of cycle. There is a in-cylinder combustion which is going on, and this happens so quick, probably you will not be able to understand how quickly it operates, and but you get the acceleration, because people only do accelerate by pressing that accelerator, but this is what goes on. More you accelerate, that means these revolutions becoming faster, it generates the power quickly. So, this most of the reciprocating engines, they are operate on this 4-stroke cycle. So, each stroke essentially, or rather each cylinder, it requires 4 strokes of its piston. So, that means 2 revolutions of the crankshaft. So, that is required to complete the sequence of events which produces 1 power stroke. So, this is required to produce 1 power stroke. Okay. Now, both CI and SI engines use this kind of cycles, and as we have seen, they are 4 strokes. One is intake, compression, power, exhaust. So, these are my essentially 4 strokes that is required. Now, what happens in each stroke? Actually, if we first take the intake stroke, so it starts at top center or top dead center TDC and ends with BDC or BC, bottom center. so which allows a fresh mixture into the cylinder. So, that means fresh mixture enters there. Now, to increase the mass inducted, inlet valve opens shortly before stroke starts and close after it ends. Now, similarly, we can see what happens in the compression strokes. Now, your both valves are closed at this state, okay, and the mixture is now compressed. So, the mixture which is within the cylinder, it is now compressed through the piston movement. Now, toward the end of the compression stroke of this process, ignition takes place. So, that is the through spark plug. So, that means the combustion is immediately initiated and the cylinder pressure increases quickly. That means the rapidly the pressure increases. So, then as soon as that happened, what happened in the power stroke or expansion stroke? So, there the piston starts at again top center and ends at bottom center. So, now since the combustion got initiated inside the cylinder, you have high pressure, high temperature gas which will, so this high PT gas push the piston down and it force the crank to rotate. So, one can think about around 5 times as much work is done on the piston during the power stroke as the piston had to do during compression. Now, the piston approaches towards BC. So, towards BC the exhaust valve opens, okay, and then the exhaust pressure actually drops down to close to the the cylinder pressure is dropped down to close to the exhaust pressure, and in the last stroke or the exhaust stroke, since the cylinder is higher than the exhaust pressure, so it allows pushing those gas back to the towards the top center. So, the piston moves towards TC. So, as this is approaches towards the TC and towards the end, that valve closes and the cycle starts again. So, this is how one go about it. So, now there could be, this is 4-stroke cycle where you have, now if you go to 2-stroke compared to 4-stroke, 2-stroke SI. So, in 4-stroke you require 4 engine cylinder and 2 crankshaft revolution. So, in 4 strokes requirement was 4 cylinder, 4 cycles, then 2 crankshaft revolution for 1 power stroke. Now, to obtain higher output for a given engine size, is simpler valve design 2-stroke cycle that uses. So, 2-stroke has simple valve to obtain higher output. So, this is also applicable in both SI and CI engines. So, it has only two stroke, one is compression stroke and second is the power stroke or expansion stroke. So, the two stroke will have only. So, one can see this is a two stroke engine operating cycle. So, what happens here? Here this is the revolution, you require only that this is the compression process. So, it starts by closing the inlet. So, this inlet is closed and the process starts and the exhaust port opens. Then the compression, the cylinder contents and draws phase charge into the crankcase as the piston approaches towards the top center, okay. And the combustion is also initiated by the spark plug. And then in this stroke, so this is combustion, expansion, ports closed. So, this is basically in the two process where you can see. Now, this is the exhaust or the rather the expansion and the power stroke, where similar to that in power cycle. So, unless the piston reaches the BC, when the first exhaust port open and this happens. So, essentially it is happening in two stroke cycle. We will actually complete this discussion in the subsequent lecture and we will stop here today.